Hello Stormwater designers, and welcome back to Clear Creek Solutions hydrology education videos. In this video, we're going to tackle what soil types are and how they apply to the world of hydrologic modeling and stormwater engineering. So that's what we're going to tackle in this video. If you'd like a free guide giving you an overview of 3 of the main kinds of stormwater modeling that we see in the industry, you can download the Ultimate Hydrology Guide in the description down below. It's 100% free if you'd like a reference tool. So anyways, when precipitation or rainfall falls on land or a project site, this is just the beginning of a long hydrologic cycle. The soil type, slope, and saturation of that soil play a massive role in how that water will drain and where it'll eventually end up. So obviously when rain falls on wherever it is, forest, lawn, grass, roadway, doesn't matter, that rainfall is going to run off somewhere. But it has to run off of a surface, right? So it has to run off of a soil type. That can be really sandy, that could be clay. And what that soil type is and what that surface is like is actually going to play a huge impact in how the hydrologic cycle is modified, because it's going to determine how quickly things can drain, how quickly water can move along the surface. So geotechnical engineering is the study of the behavior of soils and rocks and their impact on civil engineering projects. And this discipline overlaps many other engineering disciplines. So geotechnical engineering is very much wrapped up in things like stormwater design or stormwater engineering, or even things like structural engineering when determining if structures can hold up, right? So the ground that we stand on is really going to impact everything else that we do in the engineering field. So it's very important that what is done in the geotechnical engineering field is taken into account in these other disciplines when we're building out projects. So testing is needed to determine what soil types are present in the ground. And the most common test for this is the sieve analysis, where we can get an idea of what kind of soil we're dealing with. And if you take an engineering course or you've gone through college, you've probably done a sieve analysis test in the lab before. But if you haven't, I'll kind of describe it here real quickly. This is a very common test for determining soil type. So what is the sieve analysis process? We'll weight the sieves empty. So we have a bunch of different sieves. We weight them, we add the soil sample, and then we sieve manually or with a sieve shaker these soil samples so they can get sorted out into these different sieves. And it's important to understand these sieves have different sizes of openings. So as the soil is able to pass through these openings, then it's small enough to make it to the next opening, and so on. This way we can then weigh all the different fractions in every sieve and determine how large the different particles were in the soil. Then we can analyze how much or the mass of each different kinds of particles were in the soil, and that can give us a determination of what kind of soil we're dealing with. So here's a map of the United States and the different soil types that are present. I understand it's a little blurred out here, but you can tell that there's a lot of soil variation in soil orders, just even in the United States. You can see up in the Pacific Northwest, there's a lot of glacial till in that area, making it difficult for soils to drain. We can see in the Great Plains is better draining soils in those areas. And then we have more swampy, saturated soils in the south and heading up towards the mid-Atlantic. And then we're kind of getting some of that till soil back again in what looks like to be the upper East Coast over there. So there's great variation. Even within a single state, there might be great variation in soil. So we always have to test our soils on a project site before we make any determination going forward. So you can see here's some hydrologic soil groups. So you can see on the left, this might be a common chart that could be used after the sieve analysis to determine how much of this soil is clay, how much of it is silt, how much of it is sand. And then using that graph, we can determine where exactly the soil falls. And then over here are the hydrologic soil groups. For group A, we have deep, well-drained soils and gravels. They really have low runoff potential, and then usually have a infiltration rate, and this is in millimeters per hour, by the way, of greater than 7.5, and have a high rate of water transmission. Then group B is moderately deep, well-draining, with moderately fine to coarse textures. It has sort of that moderate runoff potential, less infiltration rate than group A, but greater than C and D. And then for group C, these are clay loams or shallow sandy loam soils with moderately fine to fine texture. The runoff potential is moderately high, and then they have a final infiltration rate of about 1 to 4. And then group D, which is clay soils that swell significantly when wet. They have heavy plastics and soils with a permanent high water table. There's going to be a lot of runoff generated from these soils, and they're basically not going to infiltrate at all, because once the water hits the clay, it very much hardens up, and there's just no way for that water to get into the soil. Also because they have a high water table to begin with, so there's just nowhere for that water to drain. And then this is an example of soil types that come in the software wwhm 2012 and how they transfer to different soils in that A, B, C, D category. So you can see cultivated crops or pasture, deciduous forest or forested, and so on. And if you look at WWHM 2012, we do have the A, B, C, and D soil types that you can enter in when modeling for your project. So let's talk about clay soils. So you can see on the left what clay soils look like. Clay is a fine-grained soil containing clay minerals, and when wet, clay develops plasticity. Clay soils overall are very poor draining, and when you combine that with a high water table, you're basically not going to get any infiltration or draining from that project site. It's all basically going to run off. And so with that understanding, you'll have to design bigger detention facilities and correctly to make sure that water is properly mitigated. Then once we get into something like sandy soil, it consists of the largest particles, so you can actually see the sand particles. And with a large particle size, the soil is fairly well draining. So if you've ever taken a bunch of sand and then poured water on top of it, you notice that the water's gonna be able to drain basically right through it, as opposed to clay where it will hit that sort of hard surface. Then silty soil, it's kind of in between clay and sand. It's an intermediate soil and has low plasticity due to its fineness. So it's a fairly fine soil. It's not going to harden up like clay, but it's not as large as the particles in something like sand, for instance. So what are our approaches to modeling? How does this impacted based on our soil types? When it comes to mitigation, designing a facility to meet volume mitigation and release rate requirements is going to be very important. This is assuming soils are not well draining. So if we have glacial till soils, it will require above ground storage and outlet design to properly release all this water that has now become runoff. And we can use infiltration to design a facility, so we can infiltrate runoff into the ground. And this is also assuming soils are well draining, such as outwash soils. And you can infiltrate into the native soil composition. So if you have a low water table, you don't have pollutants around, you can go ahead and just drain and infiltrate that water back into the soil. But if you don't have soils that can do that, like glacial till, which is more clay-based, you're not going to be able to do that at all. And you're going to have to develop mitigation facilities instead. So the process of accounting for soil types in stormwater design is as follows. First, you're going to have to run all those tests, right? Sieve analysis being one. There's many other tests as well to determine what kind of soil you're dealing with. Then determine exactly what that soil is, how much there is of it. Use calculations to determine what the runoff situation is going to be like, how much it's going to be able to infiltrate. And then you can finally analyze your final result in your software for how big your detention facilities are going to be and what kind of design you're going to have to approach this project with. So it is difficult to model facilities for certain soils that are well draining. And so in this case, modeling an infiltration facility is much more effective. So in something like Western Washington, where the soils are basically all outwash and it's going to drain, you might want to design an infiltration facility instead of trying to build an above ground mitigation facility. So wetlands contain soils that are heavily saturated and may be difficult to account for. So in Western Washington, wetlands are protected during the development and design stage of a project based on the amount of volume flowing into them. And we'll have a separate video covering wetlands, what exactly they are, and how we can go about protecting them, but they do have a unique soil type as well. So a correct understanding of project soil types will lead to more accurate and sustainable designs, and the misclassification or inadequate testing will not give engineers and stormwater designers enough information to properly model facilities. So if you have the wrong soil type going into your project, you're not going to design the facility properly because it's not actually going to simulate what the real life conditions are on the project site. So that's why it's very important to determine these things. Here's some of our references. As I said before, you can get that free Ultimate Hydrology Guide in the description down below. Thank you so much for watching. If you have any questions, go ahead and leave a comment. And anyways, we'll see you guys next time.